Welcome to another topic of analysis of experimental data, ETS 4502, metrology and instrumentation. Today I'm going to concentrate on uncertainty analysis. Before I go on, I want to remind everybody of the prerequisites for this course. The reason I'm doing this is because I feel that some of you guys have not gone back and refresh some of the prerequisite material that you're supposed to learn from your other courses. Remember, there are reasons why each course has a prerequisite, or in this case, more than one prerequisite, which is 3 of them. And that is, you need to be familiar, you need to satisfactorily know about the topics that are provided in these previous courses. That would really help you in this course. And again, if you need to just freshen up on some of the material that you've had previously, refer to your previous books, or try to pretty much go back to your notes and review some of the material that you have previously covered in your previous classes. That would make your work a whole lot easier for this class. The objective of our today's discussion is how to actually calculate uncertainty in experimental analysis and how to reduce uncertainty in experimental analysis. The subsequent lecture that is provided to you would include an example, and that would help a lot when doing some of your lab work and learning the material much more efficiently. So let's talk about the uncertainty analysis. As you know, with any function that we have discussed so far with any kind of a measurement that we do, we would extract some data. There is definitely uncertainty associated with each of this parameter. So every time we do a test, there is uncertainty associated with that. If we repeat that test multiple times, each time we would extract a number, and in order for us to reduce that uncertainty, we would look at this data collectively, and that would reduce the amount of error in most cases. And some tests may not be true, but when we extract this data, there is uncertainty associated with that. When we combine this data into an equation or into some kind of an analytical form, then we need to consider each variable and the uncertainty that's associated with that variable before we can take a look at the entire equation and say, now, what is the uncertainty that's associated with the analytical form of that equation? So let's say in general we have the result R, which is a function of more than one independent variable. In this case, n variables. As such, we would express the function R as the way I presented here and marked it as 1. So that was a general form of that equation. It could be a product of different independent variables. It could be an additive function. I'm going to get into those shortly, but if the function is of the general form that I've just shown you, then in order for us to come up with the uncertainty, which is, this uncertainty is the result of the uncertainties that are associated with each x1 through xn, and we call that W1. So let W sub r be the uncertainty in the results, and W1, W sub 1, W sub 2, and W sub n be the uncertainty in the independent variables. Okay, so far so good, right? So if the uncertainty in the independent variables are all given with the same odds. Again, I repeat, in order for this equation to be as accurate as possible, the uncertainties in each of this independent variable should be given with the same odd. In reality, that is never the case. And that's why even with this formula, there is some uncertainty associated with that, but it is very small in most cases, and we can neglect that. So uncertainty in the result having these odds is given as the following equation. Remember that W sub R is the uncertainty in the results, and the W sub 1 through W sub n is uncertainty in each of these independent variables. This is called the square root of sum of the squares. We take partial derivative with each variable at a time, one at a time, and then we multiply that by the error or uncertainty that's associated with that. And then we square it for the next one, again, depending on the number of variables that we have. We may end up right here if we only have 2 variables. If we have 3 variables, then we're going to have partial R with respect to partial x sub 3, W sub 3, to square that, and we take the square root of these 3 terms and so on. But this is the general form of the equation. So it's also important for the person that's conducting the experiment to be familiar with the data that is associated with that. It's like a good mechanic can spot even sometimes with a small noise that comes from a car, can detect, and that is most likely would be from this and that, and it could be as a result of this and that. Maybe not a very good analogy, but that's the best one that comes to my mind. So our experimentalist, the person that extracted data, performed the test, and do the experiment, it's important for them to have some kind of an experience with the data and the error that's associated with that. What if, again, let's look at case by case. On the general function, I just discussed that. That's the general function, but let's look at particular cases and take a look at uncertainty for product function. Product functions are the functions that are the result of there still depends on the variables, but these functions are the variables are multiplied, or some kind of some shape of a multiplication, some kind of multiplication. X sub 1 in this case to the power a sub 1 multiplied by x sub 2 to the power a sub 2, and so on. And if we have n independent variables for a product function, all these variables are multiplied. A sub n could be 1, it could be 20, it could be really anything. But and that's so don't be scared of seeing this equation. It's really nothing but if a sub 1 is 1, it's going to be just x1. A sub 2 is also 1. It's going to be x1 by multiplied by x2, and so on. So don't be scared by the look of these functions. Try to understand what's the meaning behind each of the notation that we provide here. So when we perform the partial differentiation, again, we need to do that, and as a result, all other variables except 1 would be constant. So in this case, when we take the partial differentiation with respect to x sub I, it could be any x sub anything really, x sub 1, x sub 2, and all the way to x sub n. All other variables are constant except this one number. So they would become the product still. X sub 1, a sub 1 multiplied by x sub 2 to the power a sub 2, and so on. All we did was just supposed to be x sub I to the power a sub I. When we differentiate, the power would be multiplied by the variable, and the power of the variable would be whatever it was minus 1. Again, it's pretty straightforward. If you look into any calculus book, it should give you that. It's really not that complicated. So if you have a function such as x sub I to the power a sub I, if we differentiate that function with respect to x sub I, the power, which is a sub I, would be multiplied by the function itself. It's like you're removing a sub I from here, and you put it as a multiplication right behind the variable, and then the power would be minus 1. You subtract 1 from that power. Really, and that's all to it in the simplest form. So we divide by r from equation 3. We divide the partial derivative by r, and we would arrive at this wonderful equation, w sub r divided by r. Remember, this is w sub r that I put a line above it, or somewhat encircle it. This is w sub r. I divide that by r, and the end product would be what you see here. W sub would be summation of a sub I, w sub x sub I, and so on. I square that, take the square root of that. Okay, so what if the function is not a product, but it is an additive function? In that case, what do we do? That makes our job a whole lot easier, because now when we take the partial derivative each time, for example, if we take it with respect to x1, all other variables are constant numbers. In this case, this is a constant number, this is a constant number, this is a constant number. They all is going to drop out when we differentiate that with respect to one of the variables. They all would be eliminated. It would drop out when we take the derivative, because there's constant number. Derivative of a constant number is 0. So they're all going to drop out, and we would end up with only one number, which is this is the variable. In this case, is x sub 1, and then the partial when we do differentiate with respect to xi, the result would be only a sub I. Again, if you go back to any standard calculus book, you would see that if you don't remember. And I'm sure many of you guys can right away look at that and come up with the answer. We do the same thing as we did, divided by r, and we would end up having a w sub r uncertainty in the result expressed in this term. One more new term I want to introduce to you here is that of standard error of the mean, SEM. It's encircled down here, and it is shown by a semi-star that I just put right next to it. So far you have seen how to calculate the mean, standard deviation, which is really nothing but the deviation from the mean of each point, deviation of each point from the collective mean of more than 1 points that's provided in the data, and then the standard error of the mean, or SEM. Please remember the acronym. It helps us a lot. Standard error of the mean, SEM, is simply standard deviation divided by square root of n. So please keep that in mind, because I'm going to momentarily talk about it. So keep that SEM in mind. Okay. So let me move on, make sure that I capture everything that I need here. Okay. So there are some key points here. As you can see, this figure is full of um, X's and check marks and all that. The reason for that, let me go back and actually refresh this page. That would help us. Okay, now we have a clean table here. These are the summary of what I've discussed. I presented here as key points. There are 3 columns that we're dealing with. The first column is this one right here. This is column number 2, and this is column number 3. The columns that we deal mostly with in today's lecture is column number 1 and column number 3. Again, it's pretty straightforward. It's really not that complicated. Let me go over this table with you real quickly because it's a very useful table that you can use when you do your lab work. So when you're multiplying a constant, again, we have an experimental result u, and the analytical form is shown as u a sub x. It could be shown as u x plus and minus y, u x of y, or x divided by y, x to the power n, that's another form, or it could be a general function of x. U is u sub x. So u as a function of x. Let me start with that. There is, for the result u, there's an uncertainty plus or minus e sub u is calculated using the following. In this case, e sub u would be d sub u partial derivative of u with respect to x, e sub x. Okay? And e sub x is the error that's associated with that particular function. For example, if you have, with that particular variable. So if you have one variable, and that is your x, your u is u sub x, or your y is y sub x, that variable would be an x, and there would be an error associated with that particular variable, which is given, or could be determined from the experiment, or it somehow would be given to you. So we multiply that error, which is called e sub x. Okay, we multiply that by the differentiation of the function with respect to that variable, which is d sub u, differentiating d sub u with respect to d sub x. Multiply that by error, and that's associated with that individual variable. That would give us the e sub u, and that would be the uncertainty that's associated when we combine all that. That's the uncertainty that's associated with the function itself, or with the analytical form, whatever you want to call it. And for each case, if the equation is in the form of u is a constant multiplied by a variable, a sub x, in that case, the e sub u squared would be a squared multiplied by e sub x squared. Again, e sub x is the uncertainty that is associated with variable x. We take that, you take the square root of e sub u, and that would give you the error that's associated with the function itself. If the experimental result is in the form of plus and minus, the equation is given here. If it is in the form of multiplying or dividing, the same way. And again, e sub x is the error associated with the variable x. E sub y is the error that's associated with variable y. When we combine it as such, that would be the result. What if x is variable is raised to the power n? In that case, u would be x sub n raising to the power. Then the result would be, as you can see, e sub u divided by u would be n multiplied by e sub x divided by x, and so on. So in this case, we actually divide e sub u, the error that's associated with the entire function u, we divide that by u. Again, we have looked at those cases before. In the next lecture, I'm going to provide you with an example. That brings me to the end of the slides. If you have any questions, feel free to contact me again. Please go back and refresh some of the prerequisites if you need to. Thank you.